Hi, guys, and welcome to today's session. This week we have a midterm, so we only have one live session. We will have an exam on Thursday, so we will not have a live session this Thursday, but we will resume next week. Okay, our live sessions. There is something that you need to be aware of, and I'm going to send more messages concerning that one too. There will be no live session also on November 1st, meaning a week from today. The reason is because I have a prior engagement to be somewhere else. Actually, I'm obligated to be somewhere else on that day. And but I will record a session for you guys. I will have it pre-recorded and I will post it on Canvas on that day. And hopefully you guys will follow the session. If you have any questions regarding it, please let me know. However, we will meet back again on November 3rd, which is the Thursday after the midterm. So this is basically where we stand in terms of our live session. So our live session after today, we will meet Thursday, not this Thursday, but the Thursday after, because this Thursday we have a midterm, and the Thursday after, and the Tuesday after I have to be somewhere else. Anyway, so this is in terms of the live sessions. In terms of the review, some of you did actually the review and completed it, but you still probably have to do more of it because you want to make sure that you are 100% ready. The review is going to expire tomorrow night. So for those who did not do the review, this is your last chance basically to take care of it, to prepare for the midterm. The midterm is actually on Thursday. So Thursday morning from 8 o'clock in the morning till 11 p.m., you will have a chance to take the midterm and either do it in the morning or in the afternoon or even in the evening, depending on your schedule. If you have classes somewhere else, if you have to be somewhere, like if you're working or if you have some other things during the day, then you can do it at night. And if you have to be somewhere at night, then you must plan for it to be in the day. My availability on that day, Thursday, namely, is kind of limited a little bit. So you guys need to be, hopefully some of you will start the midterm immediately after 8 o'clock because I will be available until like 11 a.m. Then after that, I have to be in a lab with another class until like 2 p.m. Then after that, I'm available until 5:30 actually, where I need to also be somewhere else. As a matter of fact, probably before that, around 5 p.m., I have to leave to go to another lab. And some of you are actually attending that lab, namely the Astronomy 125. So from that time, basically after 5:30, I will not be able to answer anything if there is a problem with the midterm or if there's an issue with Canvas or something. So this is basically in terms of the stuff that is coming. In terms of the content, up to unit 24, basically everything is testable. I mean, not the first midterm. The first midterm is gone. So the second one, which really deals with the solar system and parts of light. So this is basically how the midterm is. So hopefully you guys are aware of that and preparing only for those contents. It doesn't mean that unit 25 is not important. It is important when it comes to midterm number 3, which is coming down the road toward the end of November or even early December. So this is basically how things are. And unless you guys have any questions, I'm going to jump into the units. So before I do that, let me make sure somebody had a question in there. For homework 5 and 6, okay. I thought I covered a little bit, but no problem, no problem. Can you remind me via messaging, because I will not be available to do anything today and tomorrow until Thursday evening, potentially Friday when I'm available. So if you don't see it by Friday evening or Saturday morning, please send me a message Saturday morning reminding me again. Sounds good? Very good, thank you. So one of you guys is asking about the homework 5 and 6, and you guys saw it in the chat, but I'm talking to the people who are not live with us, that about homework 5 and 6, basically videos. And although I think briefly I discussed some of them, but no problem. I will upload probably something like half an hour or 20 minutes or so, going through each and every one of those homework problems. Hopefully by Friday, if not, one of you guys, hopefully all of you, not only her, will remind me. Okay, so that's everybody else is on the same boat. Anyway, so let me share Unit 25 with you. But before I do Unit 25, I really want to check what's going on with this week to make sure that the model looks good and there is no problem in it. Yeah, I need to share that link anyway. So because there is a link on it that you guys are. Okay, so let me go back. Share this week. Okay, again, we are in week 11 now. This is a regular start class. So the units we're covering are 25, 51, and 52. So unit 25, as I was saying earlier, is not part of the midterm, but it's part of the next midterm. And again, the midterm is actually this Thursday. That's when it's going to be available for you guys, and it's due on that day. And this discussion session is going to be here. But the reason why I came in here is for this link, because we're starting the Sun and NOAA, which is the National Oceanographic and Astrophysic Administration. Basically, that monitors everything that has to do with the weather and all of that. One of the things that they do, they monitor the sunspots, which were going to be part of this units 51, 52, and I think even 53, and so on and so forth. And the reason why it's important is because it really could be of a big, basically catastrophic implications. So that's why they monitor it, and the sunspots on the sun, and we're going to discuss that more in detail, are regions basically of a lower temperature where the magnetic field basically curls inward of the sun. And those ones, they tend to grow and shrink, and their growth and shrink is associated with activity here on Earth that could lead to basically solar flares that could reach all the way to the Earth and beyond. And if we are really in their path, they could disrupt basically our telecommunications, they could disrupt our satellites. But if the intensity is high enough, they could actually have civilization ending consequences, meaning that everything that relies on electronics, and everything does nowadays, will be fried, including the electrical circuits, including the telephone system, including the cars that have any kind of electrical component in them, and all of them do nowadays, including buses, trains, trucks, everything, airplanes, transformers for power everywhere, including the entire power grid basically for the planet, factories, everything could potentially, under high enough intensity of these things, could be brought to a standstill, and in civilization as we know it today. And basically it would take a long effort to bring it back, probably decades, if not more, to recover from it. So the last time this happened was in 1800s, and it fried really. At that time, the only thing what was available was the potentially, yes. Actually, we're overdue for it. Yes, we're overdue for one of this. Last time it happened in 1849, and that was the only thing that was then at that time were the what do you call it? The Morse code, the Morse things. What do you call them? Those, not telephone lines. Yeah, the telephone lines, but they were used for not for phone calls. Basically, they were used for the telegrams. So yeah, it fried a lot of them. But nowadays, the consequences are far more devastating, and if it happens, and potentially it could happen anytime now, we're overdue for one of them. And that's why NOAA actually is monitoring these things. And this is actually on August 16th. There was a growth of this sunspot in here in this lower corner of the sun that grows several times the size of the Earth in quickly. So of course they have to monitor it and see where it's going. Okay, and hopefully the plan is to shut down the entire electrical grid beforehand and shut down all of the electronics and warn all the planes to come down immediately. Because if it happened and you are in the plane, well, you can imagine what could happen to the plane, okay? Because it has all kinds of electronics. So that's really the plan, because it takes several hours basically for it to reach Earth, because these are particles, it's not light, charged particles moving extremely fast, and they could, but not as fast as the speed of light. And it basically takes light about 8 minutes to reach us. This one takes several hours before they reach us. So hopefully a warning will go worldwide so that everything will be shut down immediately, and hopefully to prevent far more devastating consequences. So again, because the unit is really important for us, so I thought I share with you that link there. And there are people who are monitoring this. Hopefully they do a good job at it so that we prevent anything that could be devastating. So let me share with you the units now. Again, Unit 25 deals with the Doppler effect. The Doppler effect is something that you experienced, I'm sure. Okay, even if you are at home and you hear the siren, you could tell if the siren is coming toward you or moving away from you, just by listening to the tone of the siren, of the ambulance or the fire truck or the police car or something like that. The way the tone basically changes in your ear, you will hear it at a higher pitch. So you know then the car is coming towards you. The frequency is higher than what it should be, really. The wavelength is shorter than what it should be. And you have an intuitive notion of what the fire truck is, because and all of these sirens are. So you can tell. You don't have to really be an expert. And you can tell when it's receding away from you, or it's moving away from you, just by the pitch again. If it is going toward a lower pitch, if it is going toward lower frequency, the wavelengths are higher and higher. So I want to spare you a little bit the detail in here, because I know that you have experienced it. If not, just pay attention to it next time around, or go to a train station and listen to how the train is incoming to you, and you will see the difference between the tones. Okay, let me ask a quick question in here before I move on. Did everyone in here, and there are quite a few of you here, experience this? Yes, no, those are the only two options. Okay, one yes. Another one, two. Come on, guys, there are more than two in here. Three. Okay, for the others, basically, I'm sure you did. If you didn't, then you just go ahead and basically pay attention next time when an ambulance is passing by, or a fire truck, or one of these emergency vehicles, and you will see what I'm talking about. You could tell. Actually, you could be blind, or you could close your eyes, or you could be not looking at all, and you can tell if it's coming or if it's moving away from you. So this is basically what we mean by the Doppler effect. So it's true for all waves. It doesn't matter what the wave is. Okay, it doesn't matter what kind of wave it is. So we're talking in the context of light, but it works also for sign. As a matter of fact, the picture in here is for a police officer, and you could tell if the police officer is approaching or receding from you, basically moving away from you. How the sound will work. Okay, let me go straight into this slide in here, because it summarizes everything. Okay, there are three things in here at play. Three things. A source, and the source is moving or not moving. An observer, which is you in this scenario, is it moving or not moving? Okay, and the third thing is the wave itself. The wave is always moving. So is it moving towards you or away from you? That is the key question. So the source in this case is depicted by this light bulb. Okay, the observer is sitting on one side of this light, basically source, whether it's in front of it or behind it, or at an angle with respect to it. The biggest angle in this case of interest to us is the 90-degree angle. Any other angle will experience partial Doppler effect, Doppler shift. Okay, the front one will see the wavelength shrinking. Remember, we had a long time ago an expression that goes like this. let me see, the wavelength times the frequency. In this book, they use the letter nu. So let me use the letter nu for the frequency too. Okay, the Greek letter nu. Okay, this is frequency. Okay, I use the letter F, but nu is fine. Is equal to the speed of light c. This is for light. For the case of sound, this is used as the speed of sound. So you know what sound what the sound speed is based on your daily experience. I know you don't know the number basically off of your head because none of us basically memorize things unless we have to. It's 330 to 340 meters per second, 343 to be more specific on average, okay? But that's the speed of sound. I mean, we know it intuitively, that's what I meant, okay? We have a feel of how fast sound travels. For the case of light, this is 300 million meters per second, or 300,000 kilometers per second. So it's used the million, so it's meters per second. So it's super fast for the case of sound. So for a long wavelength like this one, the frequency is low because the product has to be the same, C. It has to be 300 million no matter which way you cut it. So if you increase lambda, nu better be small. This is the frequency, the Greek letter nu, okay? Better be less, very small. For a short wavelength, for lambda small, then the frequency has to be higher. So in this case, you're sitting in here in front of the wave. As the source is coming toward you, then in this case, the frequency will be a higher frequency, meaning the wavelengths are shorter, as you can see them in here. And the color will shift towards the blue. It's not mean it's blue, it shifts towards blue. Let's say, for example, this is how the spectrum of this light bulb is. Let's say, for example, it's emitting here in the yellow. I mean, in the yellow, yes, it looks yellow to me. It's here the yellow. Here is where the blue light is, and here is where the red light is. Instead of sitting in here, it will appear to you to look like this wavelength. It's still blue, yellowish in color, but slightly closer to the blue than its normal location. On this side, though, it's going to look shifted toward the other side, meaning this is how it looks like. It's still yellow, or yeah, slightly kind of reddish a little bit, the way that I described it in here, because I shifted far more to the red, because it's moving away from you. So this is blue shifted. It's not mean that it looks blue. It's still kind of yellow. This is red shifted. It could potentially look red if this thing is moving super fast away from you, moving too fast that the band that was sitting in the yellow is actually sitting in the red. So it will look red. If it's moving too fast towards you, super fast towards you, it's going to be actually looking blue. So that's basically what that means. It shifts in color, but not necessarily mean that it's that color. It could be if it's moving so fast. Now, for an observer sitting at 90-degree angle, that person will not see it shifted at all. He will see the color all the time. It doesn't look shifted at all because it's not coming towards him. It's not moving towards him. It's moving at an angle of a 90-degree. So it's not coming, it's not moving away. But any other position, like in here, it's slightly shifted toward the red, and here it's slightly shifted towards the blue. As a matter of fact, depicted in here as green, and in here as kind of orangey. Okay, so that's basically the idea behind the Doppler effect. So what's going on in this case? The source sends a wave front, the first one, and then moves in the second, sends the second one. So every period where it's supposed to send another wavefront, had it been sitting still, it sends one wavefront and another wavefront. But it moves toward the wavefront and sends another one. So the distance, the separation between wavefront and wavefront shrinks. And that's why you see the wavelength is less and less. And here on the other side, it's the opposite. The car was supposed to send one wavefront, and after a full period, full cycle, it's going to send another wavefront. But instead moves away and sends the second wavefront. So the distance between the wavefront and the wavefront is bigger. This is one wavefront, one peak. This is another peak. This is another peak. So the separation between peaks in here appears to be larger because the source is moving away while it's doing that. So all of this entire Doppler effect could be summarized in here. This is the formula, though, that we use to find the relative speed with respect to u. I mean, we are moving. We are on planet Earth that is moving, and Earth and the entire solar system is moving and moving super fast around the galaxy. Another star, for example, could be moving, but moving faster than what we do. So let's say, for example, the entire sun is moving around 300 kilometers per second. And these people are moving 400 kilometers per second. What this formula gives you, it doesn't give you how fast this star is moving. It gives you the difference between the two stars. It tells you that this star is really moving with respect to us by 100 kilometers per second away. Had it been moving towards us, let's say, for example, 300, no, 300 is not good. Let's say, for example, moving 500 kilometers with respect to us, and we're moving towards it. Well, the relative velocity in this case is 800 because we're moving towards each other much, much faster than. So the relative velocity in this case is 500 plus 300. Had it been stationary, the relative speed would be only 300. So that's basically what it is. Even if it's moving away from us, let's say, for example, by only 200 kilometers per second. So if we're moving towards it by 300, and it's moving only 200 kilometers per second, so we're actually approaching it. We're approaching each other, basically. The distance between us is shrinking. So in this case, it's going to be blue shifted to some extent. And because it appears to be moving towards us, because we are moving towards it. Here is the case, for example. You have a source. And if we're moving towards a source, it's going to be blue shifted still. And we are moving towards the source in this case, so it's going to be blue shifted. So this formula here, the bottom line is it's not going to give you the exact speed, the absolute speed is going to give you the relative speed. Okay. And it's the difference in wavelength between what it should be and what it is. So if this wavelength, for example, theoretically, it should be, let's say, for example, 600 nanometer, but when you measure it, you find it 400 nanometer. So it shrunk by 200 nanometers. The difference, you plug it in here. Divided by what it should be 600, then it's going to be negative 200 divided by negative 600 or negative 2/3. Negative 2/3 times the speed of light, so it's going to be negative 2/3 the speed of light. That means it's coming towards you by 2/3 the speed of light, by 200,000 kilometers per second. This is super fast, ridiculous fast. But remember, the speed of light is 300,000 kilometers per second or 300 million meters per second. On the opposite side of the equation, if you are on the other side and it's supposed to be 600 nanometers and you measure it and you find 700 nanometers instead, so the difference is 100 nanometers, so it's going to be 100 nanometers divided by what it should be, which is 600 nanometers, times the speed of light, which is 300,000 kilometers per second. Then in this case, of course, this is 1/6. 3 divided by 6, that's 1/2. So it's going to be what? 200,000 kilometers moving in the opposite direction. Did I do it correctly? No, it's I'm sorry, 3/2. So it's going to be only 150,000 kilometers per second moving away from you. The bottom line, the sign of delta lambda determines exactly if it's moving towards you or away from you. This is all there is in this unit, really. Okay, for those sitting in Astronomy 125, they will remember the example that I'm going to give because it's actually from their lab. So I'm going to share with you their lab that we did a long time ago. If I can find it, here it is. Let me share it with you. Share this lab. So this is part of the lab for Astronomy 125. Of course, this purpose of it is not the actual lab, it's just this calculation. This is the same expression that that we're talking about in here. Find the speed. The radial velocity of a star can be determined from the Doppler shift of the lines of the spectrum. This is given by this expression, which is exactly what it is. So delta lambda in the expression that I showed from the book is nothing but the lambda minus lambda naught, where lambda naught is the actual frequency that you're supposed to have. Okay, but lambda is the measured value. Okay, so where lambda naught is the unshifted value when the velocity of an object is 0. So this is basically a stationary object emitting it, like light, for example, in the lab. So you go through the spectrum, for example, of hydrogen, and you measure its spectrum, and you, in this case, you measure its wavelength, and you find it a number. Well, the light in this case is not moving away from you, so that's lambda naught. Okay, the observed wavelength. So that's what you observe. That's what you calculate. That's what you measure. I'm sorry, is the shifted wavelength of the object in motion. Find the radial velocity. So in here it gives you an example. A star observed to have an H alpha line. This is a spectral line. Lambda naught, which is supposed to be 656.30 nanometers at a wavelength of, this is what they measured, 656.52 nanometers. So instead of 656.30, they measured 656.52. In other words, 0.52 minus 0.3, so it's going to be 0.22 nanometers. That's the difference in the shift. Divided by this number, divided by lambda naught times the speed of light. So let me go quickly to my notes in here and do the calculation so that you guys understand how that works. Go my notes. So again, we're trying to find the relative speed, how far this star is moving away from us. So we're measuring V relative with respect to us, and we're saying that this is the wavelength minus the unshifted wavelength divided by the unshifted wavelength times the speed of light, which is 300,000 kilometers per second. Okay, they say that the actual wavelength should be this number, but they measured it to be this number. So this is lambda naught. This is what lambda is. So if I take lambda minus lambda naught, obviously is going to be 2 minus 0, 2, and so it's this minus that. Okay, so this is the one in the after the negative sign. So 5 minus 3, that's 2, and 6 minus 6 is 0, and the whole thing is 0. So this is 0.2 nanometers, and I want to find the relative speed. So it's 0.22 nanometers. That's the difference between the two wavelengths, divided by 656.30 if we want 2 nanometers. The nanometer cancels the nanometer times the speed of light. Let me pull a calculator quickly in here. Calculators here. And let's do this calculation. Hopefully you guys are doing, again, doing numbers is really helps you understand a lot of these concepts. So please don't be shy, don't shy away from these things, okay? So let me share with you. So it's 0.22 divided by 656.3, and this is the ratio. Okay, it's 10 to the negative 4, by the way, when you see it something like this. So it's a very small number because the numerator is small, the denominator is big, so it's a small number. Times the speed of light, which is 300,000. This is 300,000 kilometers per second. So the answer is going to be in kilometers per second. This star is moving away from us at 100 kilometers per second. This is ridiculous speed, by the way. Okay, this is a ridiculous speed. I mean, yes, it's the way the shift in wavelength is small, but look, the speed with which this star is, and it's moving away because the newer wavelength is higher than the original wavelength, meaning that the longer wavelengths, so the frequency is less and less in this case. Okay, so in this case, it's the relative speed is about 100 kilometers per second, which is tremendous speed. So if you want to know how many that in hours, you multiply this by an hour, because an hour is 3,600 minutes. So this is going to be 3,600 and then 2 zeros. So this is 360,000 kilometers per hour. This is a ridiculous speed. Every hour it's moving 360,000 kilometers. Multiplied by 24, and you will have a ridiculous number per day how far the star is going to get every day away from us. Okay, so this is actually a good practice number. There is another one I'm going to lift it for, and I'm going to leave it for you guys, but it's actually worth also doing it on your leisure time. So the second one is actually gives you a galaxy observed to have a calcium K line, lambda naught, which is supposed to be 393.40. This is the blue light, okay, at a wavelength of 445.85 nanometers. This is a tremendous speed you're going to find, because you're going to take 445.85, subtract from it 393.40. So the difference already is 45 plus 7, that's 51 point something nanometers, divided by 393.4. and multiply it by the speed of light, you're going to find that this galaxy is moving at an incredible speed. This is basically how the James Webb also is doing. Although when we get into this one later on, we're going to have a different definitions to use the Z number, which is actually the Z shift, which measures the shift of the galaxies. So this is unit 25 in a nutshell. The biggest formula from unit 25 is how to find the relative speed using the Doppler shift. The Doppler shift is the difference between the wavelength, the measured one, and the actual one, divided by the actual one times the speed of light gives me how fast the star is moving. By the way, this is the same technology used by the police to basically catch speeders. Okay, they use a radar gun that sends sound waves, because light is ridiculous in this case, although they may use the light too. Sound waves, and based on the Doppler shift, again, they can find the how fast you're moving. Okay, they can find how fast you're moving, and you can be given a ticket, and so don't do it. Okay, so this is unit 25. Any questions about unit 25? No? Okay. So let me share with you unit 51. Unit 51, now we are really getting into the sun, hence that link that I provided you. So describe the features and the properties of the layers of the sun. So the sun, we see from it the photosphere. That is the side of the sun that we see. But the sun is actually have different layers inside. If you look at the color of the sun and use the Wien displacement law, basically, that gives you the wavelength, the maximum wavelength, as compared to is it 2.9 or 2.6? I always forget the decimal points. I think it's 2.9, 2.9, yeah. Times 10 to the power 6 divided by the temperature. Not 10 to the negative. Okay, so again, let me go back into, let me give you the correct formula from the power. Yeah, 10 to the power 6, yes, correct. Okay. 10 to the power 6. So, that was it. Yeah, 10 to the power 6. The main thing in here is this is the temperature for the sun is 5800 Kelvin. That's the surface temperature of the sun. From here, you can find the wavelength. This formula works only and only if the wavelength is in nanometers. Okay. So this is Wien displacement law. After you find the displacement, after you find the wavelength, you will find that the sun has a specific color. And that color is this yellowish color in here that appears to us to be yellowish color, but it actually a little bit max toward the green, which is a mixture of all of the other lights. So it gives us the impression that the sun looks white. So this is the photosphere. If you look up close to the surface of the sun, you can compute how much basically you can find, again, the surface of the sun has this temperature of 5800 Kelvin. 5800 Kelvin is not that high of a temperature for nuclear reactions to happen. If you are inside the sun, if you go all the way to the inside of the sun, then the temperature there is high enough for nuclear reactions to happen, which is part of the discussion for the next units, okay? To the nuclear processes inside the sun. The surface of the sun is boiling with this layers, and it looks like basically the surface of water when you boil it, and that's exactly the process similar to what is going on. So basically there is convection going on inside the sun because the lower layer is at a much higher temperature than the surface temperature of the sun, and those temperatures, they have to go somewhere. So basically the gas with which is mainly the sun is mainly a gas in this case, which is mainly hydrogen and helium, okay? And those are the two gases existing in the sun. So the upper layer is cooler, the lower layer is hotter. So in this case, the lower layer will rise because it will have lower density, and the higher layers, because it's cooler, will fall because it has higher density, and the process revolves like this one. So this bubbles that form, and this is how the surface of the sun would look like. The surface temperature is about 5800 Kelvin. There is a slight variations in temperatures here and there, and that's where the dark spots actually appear because they are actually a lower temperature than the rest of the sun. Okay, so this is basically what's going on in there. Obviously, because they're lower temperatures, they need to be sinking further into the sun, than the higher temperatures, and that's what's going on. So this is basically the surface of the sun. So in terms of the characteristics of the sun, first of all, the distance between us and it is 1 astronomical unit, which is about 150 million kilometers. How did we determine that? Using radar at this point. There are other techniques we used in the past, but now we know this number far more accurately. Okay. The radius of the sun is about 700,000 kilometers. It's actually 690 something, 96,000 kilometers, which is puts it about 10 times the diameter of Jupiter, which means that you take Jupiter, and because it's 10 times Jupiter in diameter, because the volume goes like the diameter cubed or the radius cubed, so it's about 10 times 10 times 10 Jupiters, or 1,000 times bigger than Jupiter in terms of size, in terms of physical size. In terms of Earth, remember Jupiter is about 11 times bigger than Earth. So Jupiter is 11 times, let's roughly make it 10 times, because it's much easier to deal with 10. And the sun is 10 times bigger than Jupiter. So the sun is about 100 times bigger than the Earth. But the volume goes like 100 times 100 times 100. So the volume of the sun is 100 times 100 times 100, and that is 1 million actually. So it takes 1 million Earths to put them in the sun. So if you take the sun and go from side to side, you're going to put basically, remember, this side from here to here, it's about 600,000, it's about 100 Earths basically. So it's about 100 on this side, 100 on this side, 100 on all sides. And if you multiply the numbers, obviously you're going to find 1 million Earths fit inside the sun. The mass is 2 times 10 to the power 30, which is about basically about 1,000 times bigger than the mass of Jupiter. It's slightly off, honestly, because the density of Jupiter is 1.3, the density of the sun is 1.4. They're very close from each other. The density of the Earth is still much higher than both of them. So Earth is the densest object in the solar system. We're not counting the density of the core of the sun, which is very high though, okay? Which is 160 kilogram per liter. So this is a ridiculous number. So what I'm talking about in here, the average density of the sun, okay? So this expression in here, the way you find it is you take the mass of the sun, which is this number, and you divide it by the volume of the sun, which is 4 pi times this number cubed. And you find this number. So that puts it on average less than the density of the Earth. However, there are parts of it, it's denser inside, and as you start to go further and further away, the temperature drops and drops, and as it drops, the pressure actually drops with it, and the gas will be more dilute. In this case, it's less dense, and at the end, on average, it's less dense than the Earth. Okay, the surface temperature is about 5,800 Kelvin, and this is using Wien's law, the one I was describing earlier from the temperature. But inside the core of the sun, inside the sun, at the center of the sun, the temperature is 15 million Kelvin. And this is a very important concept in here because of the fact that this temperature is high enough for nuclear fusion to start to happen. So you'll have a hydrogen combining with another hydrogen and another hydrogen and another hydrogen in a very long chain. So it's not immediate. It's not like 4 protons come together and all of a sudden you have helium. So it's really a long process, because helium, for example, has 2 protons and 2 neutrons. So in this case, what's going on? 2 of the protons basically change nature and become neutrons. So we're going to talk about the proton-proton chain that is happening in the sun, and there is another process actually they call the nitrogen carbon oxygen cycle also that results in the same fashion, creating helium basically out of hydrogen. So the composition that you see in here, that's mainly hydrogen and some helium in it. Forget about the 2%, which is just a fraction of the overall composition of the sun. Is really a changing number because of the fact that the sun is converting every second a lot of hydrogen into helium. So this number is changing. So the sun at some point will run out of hydrogen in its core, in which case basically this process ends. And the sun basically will shed the outer layers, and whatever left is going to be a white dwarf. So that's basically the life cycle in a nutshell of the sun. So as long as it has hydrogen in the core to convert it to helium, the sun is good. And at some point, it's going to run out of it. So what it's going to do is going to run through some crazy cycles involving the hydrogen inside the shells above the core of the sun. And that process will continue where the sun swells so big and becomes actually a red giant. And then at some point, we'll even run out of that hydrogen and then start fusing helium. But then after that, it's going to run out of steam and basically shed the rest of the gas and become a white dwarf and start cooling from that point on. It will become a black dwarf. So this is basically in a nutshell what this is. Now, the output of energy from the sun is 4 × 10⁻26 watts. It's a light bulb. But unlike the light bulb you go and buy from the store for 100 watts, this light bulb is really 4 × 10⁻26 watts. That's all. But it doesn't use electrical energy to convert it into that. It uses nuclear energy. It uses this process I was describing earlier, okay, to output this much energy. Okay, how did we find this number in here? Well, 2 ways you can do it. One way, go and make a big swimming pool, okay, or even a square meter of it, okay, of water, and see and measure its temperatures now, okay? And wait for an hour, for example, and measure its temperature. Obviously, if you expose it to the sun, its temperature will rise, but if that's the only source of heat for the water, then in this case, you can find how much rise in the temperature of the water. So from here, there is a formula in the heat thermodynamics, actually, in how heat is transferred into water, where you take the amount of water that you have in here, which is the mass of the water, times the specific heat of water, which is 1, so this number is 1, times the change in temperature. So how much the temperature went from one place to another place, that's really the whole thing. And how much water you have in it. So you're going to get the amount of heat that this thing was received in terms of energy in 1 hour, for example. So that gives me the amount of heat that I can measure for that pool of water, depending on how much mass, of course, I have. That is for 1 hour. So I can divide that number by seconds, and I will find how much energy is received per second. Basically, the wattage on that square meter, how much it is. Okay, how many watts on that square meter. Then I have to take that number and multiply it by the distance from the Earth to the sun is 150 million kilometers. So the radius in here is 150 million kilometers. Times 4 pi r squared, because all I did was collected on a square meter. So I need to find the entire energy that was outputted for the entire sphere where I am sitting, where the Earth is. Here is where the Earth is, but there is a big sphere in here of radius 150 million kilometers. So if I use the algebra correctly, okay, then I can find, because all I did was I found it for a square meter. That's how much I measured. So I need to find for the entire area. Once I do that, I should find with a big number, something like this one. That's a technique. There is another way also of doing it also to find the how much we can do. All we have to do is use Wien's law, Stefan Boltzmann law that tells me how much energy is going to be outputted. Remember, it's a constant, which is 5.67 times 10 to the negative 8 times the temperature to the power 4. Remember, the temperature, we found it to be 5,800 Kelvin. This gives me, but remember, I have to multiply it by itself 4 times, 5,800 times 5,800 times 5,800. This gives me how much energy, basically, the sun is going to output in per square meter. The power per square meter. So I have to, again, multiply it by the radius of the sun squared, which is this number times 2 pi, times pi. 4 pi r squared, I'm sorry. And that's it. So 2 ways to find this number, but it's a ridiculous number. Okay, you need to remember this number because down the road, we're going to be computing the luminosity of other stars. And we are always going to refer to them how they compare toward the sun. So when I give a number later on, and we say it's 4 times luminous as the sun is, what we really mean is 4 times 10 to the power 26. If we say, for example, it's a 10th luminosity of the sun, that means that we take this number and divide it by 10. It's going to be 4 times 10 to the power 25 in that case. If it's 100 times more luminous than the sun, it's really 4 times 10 to the power 28. So this is going to be a reference for our discussion from this point on when we talk about other stars. So any other star, we're going to refer to how luminous it is versus the sun. So the sun is going to be the unit from this point on, just as much as the distance between the Earth and the sun became a unit for us for measuring how far, for example, Jupiter is from the sun. We said Jupiter is 5.2 astronomical units. So what we really mean is 5.2 times this number, 5.2 times 150 million kilometers. It's a kind of easy way of trying to work their way upwards. So this is some of the things. And the luminosity is a big number because there are two things you have to distinguish between. There is how bright an object is, which is a brightness. And there is the luminosity. Luminosity is how much light is actually is giving. Brightness, how it appears to you. Obviously, it appears to you depending on how far it is. You could have a star that is 100 times more luminous than the sun, but it appears dimmer than the sun. Why? Because it's far away. And all of the stars appear dimmer than the sun, all of them, with no exception. The sun during daytime outshines any star whatsoever in the sky because it's much closer to us than any other star. So that's why the brightness and the luminosity are two key concepts down the road. Okay. So let's get into this, the inner structure of the sun. So we have the core. This is where the nuclear fusion happens. So from this point on, when we talk about core of stars, we're referring to really this region of the star. Then there is this radiation zone. This radiative zone is when light is going to travel to work its way to come out to the upper surface. This is light coming tremendously from the core. This is a hot region. Then in this case, this is a zone of convection. This is what I was talking about. The lower region is hotter than the upper region, and it boils up and comes down, boils up and forms these bubbles around the sun. Then you have the photosphere. The photosphere is the upper layer that we see, and this dark regions on it, these are the sunspots, and the sunspots in here have this regions of twisting and binding, basically magnetic field lines that snap at times, and when they do, they take with them a lot of materials in all directions, and those materials, those are the ejections that come to us in here. Okay, so this they become very, very damaging if in case they reach Earth, but they snap in every other direction, so it's not like they go all over the place. Okay. So we have to really be in their line of sight to be able to be subject to their effects. You have the corona, which is visible during a solar eclipse. There is one that happened today in Europe and Northern Europe, actually England and all of the other places. In here, we didn't experience it. So the corona, and then this is the corona, or the outer layer in here. The particles are coming super fast in here. The temperature, as a matter of fact, is super high in here compared to the surface temperature of the sun. But because of the low density in here, you don't see these temperatures in here. So this is basically the entire structure of the sun and how it looks like in terms of the composition. How do we know all of these things? Well, part of it, we study the quakes on the sun, or the sun quakes. Okay. So there is a seismology, so basically trying to listen to the different murmurs of the sun and how it's beating. So that gives us the insight of it, and that's how we know a lot of the information about the sun. Okay, of course, numerical simulations also help a lot because it really confirms to what we say. The distance from here to here is 700,000 kilometers. Okay, that is the radius of the sun. Again, so the photosphere is what we see. Its surface temperature is about 5,800 Kelvin, and the photosphere is a very, very thin area of the sun. I mean, to be more specific, 5,780 Kelvin. So what's going on in the sun? Basically, there are two forces at play. Okay, radiation trying to leave the sun from the heat. The inside is hotter and the outside is cooler, so it's trying to get rid of its heat. So this is a balloon, for example. If you raise its temperature inside, for example, the bubbles underneath, how they form, if you raise the temperature in the oven, the water starts to rise, the gas starts to rise, everything starts to evaporate. This is a law known for the gases, the ideal gas law, which says that the pressure times the volume of a gas is some constant number, which is the number of moles, basically how many moles you have in here. For those who do chemistry, they're familiar with this expression. If you didn't, don't worry about it. Just this is constants. Both of them are constants times the temperature. The volume usually hardly changes in the beginning. So the pressure in here is high with a higher temperatures. Remember, the lower regions of the sun are hotter than the outer regions. Therefore, the pressure inside is higher than the outer regions. So there is an outward pressure trying to push the gas outward. So the sun is trying to explode, really, and there are all of this nuclear fusion inside of it, and that is the effect of it. But on the other side of the equation, there is a gravity. Gravity is trying to pull things inward. So gravity is trying to pull this way, and the pressure is trying to push this way. When you reach a balance, in this case, you are in good shape. If you shut down the nuclear fusion inside the sun, then the sun starts to compress. If it slows down somehow, if there is less nuclear fusions, for example, inside the sun, then it starts to shrink in size. And what it does in this case, when it shrinks inside temperature starts to increase, because higher pressure causes higher temperature. Higher temperature will increase the rate of reactions again. So the temperature inside becomes hotter and the pressure starts to grow, in which case the balance is restored again. So the sun grows in size again. So you see that the balance in here, if you shift it one way, it's going to shift back. So it stays intact, it stays perfect. So there is a balance right now. So you really have to think about the process. If somehow the nuclear fusion slow down, there is enough pressure to cause them to increase so that the balance is restored. And the sun stays as is. When it runs out of fuel, though, there is nothing to hold it back. And it's going to start collapsing due to the force of gravity. So that's really, in a nutshell, what's going on. So this is a depiction of it. In the upper layers, of course, there is less gravity because of the fact there is less gas on top. But the temperature is not that high either. So there is less pressure, and the two are in perfect balance. As you go lower and lower into the sun, there is more and more material that is coming, causing more gravity inward, but there is more temperature causing more outward pressure, and the sun is in balance. It's still at least good, as long as there are nuclear fusions in it. So this balance is maintained as long as the nuclear fusion is happening in the sun. And this is the ideal gas law I was mentioning earlier. Pressure is some constant times temperature times the density. The density part of it, so the way I wrote it, is PV equal to nRT, which is how it's known for chemists everywhere. And actually, that's how it's used. You can divide by the volume, and it's going to be N times R divided by the volume. And N is the number of mole, which is related to the mass. So the mass per volume is actually the density. So this is density times some constants. The constant in this case, R, is number. Think of it as just another number, okay, which is 8.314. Just a fixed number, constant, doesn't change. This is what you find in the lab if you want to. So don't think too much about the constant. What matters really is the temperature and the density, of course, okay? So that's basically in a nutshell what's going on in this case. How did we learn all of these things? As I was saying, helioseismology, that's basically the quakes on the sun or sun quakes. Okay, I mentioned the convection zone. There is a radiation zone, and light, when it's a photon, when it's born inside the core, because that reaction that I described earlier for you guys into how the, was it in this file? Just in this here, yeah. The proton-proton chain will produce light, will produce basically energy in the form of light. And that light is going to be a very, 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 very high frequency. You cannot see it. But by the time it leaves the sun, it becomes indivisible. So what's going on inside in here is that light will bump into the electrons that are flowing. Remember, this is a high temperature to the point that the gas hydrogen is not gas at all. It's in a plasma state, meaning it's not it's completely ionized, meaning the protons by themselves and the electrons by themselves. So light now that just feed from the produced from this chain. So you have 4 protons coming together and combining to give you helium plus light. The symbol for light, you guys will get to know the Greek letter gamma. That's how they use it actually, they represent it in this case. But this light is so high frequency, it's not in the visible range at all. So, but that light will come in and bump into those electrons. And when it does, its wavelength lengthens. In other words, its frequency is shortened because it loses energy in the process of colliding with an electron. That there's more. So it's going to collide with another one. It's going to shrink further and shrink further in wave in frequency, increasing wavelength, and then it's going to work its way through the core, and it takes about 100,000 years because it finally makes it out of the core. When it does, it straight through this and then goes through the convection zone, and then it's going to go through the upper layer in here in this case, and then it's going to reach us in about 8 minutes from that. It takes a long time in here, trapped inside the core. So the light that you see outside right now in your window or in your room, wherever you are, is actually happened or was produced in a nuclear reaction that happened hundreds of thousands of years ago. So the photon that just landed on your skin or went captured by your eye took so many years before humans evolved into the form that we know it today, before it reached you. There is a key question in here now, and it's a very important question. How do we know all of this? If this light, the one that tells us basically about the core of the sun, what's going on in it, let's say, for example, today, for the sake of argument, the sun becomes more active, produces more light, okay, inside the core. Of course, we will not know it if it was up to light only until 100,000 years from today. That's something weird is going on in the sun. That's basically the problem. Or it slows down. It's not necessarily speeding up. Let's say, for example, the rate of the nuclear reactions inside the core drops, and there is less light is coming out. So instead of knowing about it today, if it was up to light only, we're going to wait 100,000 years. There is another byproduct that's going to save us from all of this trouble. And that product is actually another particle in here called neutrinos. And the neutrinos are going to come out unimpeded. They don't interact with the electrons whatsoever. They come from here straight up, and they can reach us in about 8 minutes. If something happens to the core of the sun, we will know it from the neutrinos. We will not know it from the light. Okay, that's why studying neutrinos is actually an important process. So 3 things are produced from the nuclear reaction that I described, and I'm really anticipating for the next unit. It's going to produce light, which we will see. It's going to produce helium, which is actually a product that is necessary in this case, and basically it causes the sun to run out of hydrogen at the end of the day. But it produces also neutrinos, and that is actually what sees the whole process and makes us understand what's going on inside the core of the sun. So neutrinos play a major role in our understanding of the sun, what's going on in it. So if something happens today, we will know it in about 8 minutes. Something is weird is going on inside the sun. So that's basically in a nutshell how things are happening inside the core. How are we doing on time? Oh, still good. Oh, still good. Still have a few more minutes. So, so this is the process of how the energy is transported and how it's going on in the sun. Again, I will leave it to you guys to read about the rest of the processes in here in the sun and the fact that it's very active. And this is actually we started with basically the coronal mass ejections, the ones that I was describing earlier. So these are magnetic field lines. So those are charged particles that leave the sun, the surface of the sun, and form this huge basically flares that go around the sun. And sometimes the magnetic field lines start, because of the rotation of the sun and the motion of the sun, they start to twist on one another and they snap. And when they do snap, whatever gas is trapped in them, namely charged particles, namely protons for all practical purposes. That's the main component of the sun, hydrogen, okay? It's going to be ejected tremendous speed and it's going to travel far away from the sun, okay? The furthest point that we know it can travel at least according to Voyager 1 and Voyager 2, which they reach the solar heliopause, basically the region where the effects of the sun starts to basically stop. That's where the magnetic field of the sun extends. And that's how far they can go. And the heliopause plays a major role in protecting actually in all of the inner planets, because there is a lot of stuff coming from the galaxy, and it's a magnetic field of the sun that deflects it away. And this is 90 astronomical units all the way to 100. And that's right now where Voyager 1 and Voyager 2 are at this point. One of them is going in one direction, the other one is going in another direction, basically leaving the solar system at this point. So this is basically some of the stuff from unit 51. Are you guys in the mood for unit 52, or should I record it and post it to you guys later on? Because it's still part of this week and we're not meeting this week. What do you guys think? Any opinion in here? Okay, let me quickly check for the units in here. I described, let me share with you first. Share 52. I described some of these processes already, and namely how hydrogen, but it's a very, very important processes that we have to go through them. So this is basically inside the sun, and how the energy is converted using the famous equation of Mr. Einstein, and how energy and mass are equivalent. Because trying to understand where the energy gets its power is really something that you really have to understand. And it's coming from this expression. C is the speed of light, so it's just a fixed number. It's 300 million squared, which is 9 times 10 to the power 16. So it's how much mass is converted into energy, really, that's all, okay? So basically the process that we're going to discuss in here, how protons come together and fuse to form heavier elements, okay? You have two protons coming together. Technically, the protons are charged particles, so they wouldn't come anywhere near each other. But at tremendous temperatures, they would be moving so fast that they will overcome this repulsion. And when they do, they form heavier and heavier elements until we get into helium. Helium, actually, we call it helium, but it's actually the alpha particle because it's still ionized. Helium is when it gains its electrons and becomes a neutral gas, helium. So again, this is the chain, and I need to really go step by step on the process. Here is what I was describing earlier. So you're going to produce a different version of helium, in this case, helium-3, plus gamma. And gamma is the photon I was describing earlier. It's the light that is produced, plus the nu, the Greek letter nu. In this case, in this book, everywhere else actually is the neutrino. So the nu that I described in the beginning, when I was describing the frequency, that is actually the symbol also for frequency. But this same Greek letter nu describes neutrinos in this nuclear reactions. So this is universal. So when you see nuclear reactions like this one in here, two hydrogen nuclei, basically proton and proton, give you a heavier proton in this case, a heavier hydrogen, I'm sorry, in this case, plus a positron, which is an electron with a positive charge for the neutrino. So in this case, the nu stands for neutrino, not frequency, okay? So hopefully that clarifies some of the confusion. I know physics sometimes uses the same symbol and gets confusing, but hopefully you're not going to get confused. And then this heavy hydrogen that is made, which is helium-2, will combine with another proton, another hydrogen, regular hydrogen, to form helium in this case. So what happened in this case in here is one of these protons changed to become a neutron, so that this will have in its nucleus a proton and a neutron. This proton and neutron will meet another proton, and you will have two protons and a neutron. This is an isotope of helium, another helium basically, because typical heliums have two protons and two neutrons. This one does not have two neutrons, it has a single neutron, but two protons, plus light. Now, when two of this type, namely two helium isotopes, 3, meet, they will form a regular helium, which is helium-4, and they release in the process 2 protons. But remember, you have 2 protons from here plus a neutron, 2 protons from here and a neutron. They form helium-4, which has 2 protons and 2 neutrons. But you remember, you started with 4 protons. So one of them goes here and the other one goes here, and the equation is balanced. So in other words, this equation actually combines 2 protons and another one that's a 3 protons from one side to produce just this one, and combines 3 more to produce this one. 6 protons altogether come in, 2 come out. So at the end of the day, only 4 protons, basically the net side of the equation, 4 protons come in and form regular helium. Here are the protons. So there is a proton, which is a helium atom. There is another helium nucleus, I should say, and another proton, which is a helium nucleus, a hydrogen nucleus, I'm sorry, and another hydrogen nucleus, which is another proton, another hydrogen nucleus, which is a proton, another hydrogen nucleus, which is a proton, another hydrogen nucleus, which is a proton. We have 1, 2, 3, 4, 5, 6 altogether. When all of this is said and done, I will end up with helium atom that has 2 protons, 2 neutrons, and ejecting from it 2 protons, 2 hydrogen nuclei. So basically, at the end of the day, I end up with 6 coming, but 2 come out. So only 4 actually effectively mix to give you helium. In the process, I gain light here and I gain light here. That's gamma rays. And I also get a neutrino here and a neutrino here. A neutrino here, what tells me basically what's going on. I'll get another light too, actually, when this positron combines with a regular electron and they cancel each other. They annihilate each other and they give me 2 lights. And that's not the only light that I'm getting, because I have a symmetrical process on the other side. So altogether, I have light here, light here, light here, light here, light here, and light here. And that's produced. So that's how light is made in the sun. Obviously, as I said before, the frequency is so high that it's not something that we can see. It has to go through the scattering with the regular electrons that exist there before it becomes long enough wavelength so that we can see, becomes visible. Okay. Plus 2 neutrinos, this neutrino and this neutrino, in addition to the hydrogen that is the helium that has formed. 6 proton comes in, 2 protons come out, and a helium nucleus. 2 neutrinos come out, and 6 photons basically emerge from this process. So that's how basically this is the proton-proton chain. This is basically what we believe is happening in the sun. How do we know all of this is true? Well, if you go and calculate how many neutrinos are really supposed to come out of the sun and go to a detector for the solar neutrinos, and you find the same number, so everything fits in the place, okay? There is the 2 experiments that I know on. One of them in Japan is by the Kamiokande detector, and another one in Canada, and they found the actual numbers. So without meaning to do so, I get into the proton-proton chain to explain basically the process, the equation that is governing all of this. If this is how basically what that equation tells me. If I add the mass of this proton, and 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 deduct from it the mass of these 2 protons and the mass of this helium atom, helium nucleus, I should say, the discrepancy is going to be in energy. If you want to, the neutrinos have negligible masses, so they don't contribute in the process. Photons don't have mass. So the decrease in mass is the energy produced by the sun. So the decrease in mass, I have to multiply by c², and that tells me how much energy is produced per process, per nuclear reaction. And there is so many of it happening in the core of the sun. So this is the entire picture for unit 52. So we're done. We don't really need to record it. Okay. So when we meet next time, which is going to be not this Thursday, not this coming Tuesday, but the Thursday after. But I will record the classes because next week we're going to be exploring other units too. Okay, thank you guys for your attention. The ones who are watching this recorded, also make sure you follow all of the announcements and also the stuff that is in this one. And I will follow this announcement this lecture with announcements on Canvas so that you guys know what's going on too, for those who are not live with us. Thank you guys. And I see some of you in the lab on Thursday, others I will see them Thursday, a week from today, week from this week. Thank you. This one.